Hi, everyone, and thanks for coming to this talk. So yeah, it's called 1 Year of Akka 2.6. I'm Sean Glover. I'm a principal engineer at Lightbend on the Akka engineering team. I maintain a bunch of projects. The Alpakka project's one of my passions here at Lightbend. I maintain that as well as Alpakka Kafka, which is a separate repo. I'm the organizer of Scala Toronto, which you might have seen this logo floating around with meetup videos that we've posted in the past. And I'm a maintainer and contributor in the Akka and Kafka ecosystems. So Akka 2.6 was released in November 2019, and Akka 2.6, the release made the typed actor API the main API. So all of the features that were released since 2.6, features in the core toolkit as well as additional libraries, they're all based on this new typed API. I'm just going to cover some of the features that I was either involved in developing or that interest me in general. They're by no means the most important things that we released or the biggest things, but I think they fit together nicely in a presentation. So hopefully I'll get through all of these in the time allotted we have here. So I expect some people aren't familiar with the new typed actor API, so I'm going to cover that first. A little history though about it. It was introduced as an experimental module in Akka 2.4.0, and that's way back in September 30th, 2015 is when that was released. But the origins of the typed actor API stretches back even further than that. I've seen references to talks that Roland was giving in 2012. The API was mainly the creation of Dr. Roland Kuhn, who is the former team lead of the Akka team. He left Lightbend several years ago to found a startup. The old actor API is now known as classic actors, and it's by no means it hasn't been displaced in any way. It's not considered legacy. We're not going to sunset it or anything like that. It's just now not the focus for new development. But you shouldn't be concerned about your systems that are implemented using classic Akka. The APIs haven't changed. And if you're interested in using Akka type, you don't need to port everything. You can incrementally start using Akka type stuff in your classic actor system because there's interoperability between the two APIs. The big difference with 2.6 is that the new API became the default for documentation and reference projects, and like I said earlier, is the base upon which all these new features that were added in the last year were developed upon. So yeah, the first thing we do typically in a actor-based system is define a message protocol. So in this example, we're working within the banking domain, and specifically, we're going to implement an account management actor. So we have 3 commands here, and they're just simple types with the amounts we want to withdraw or deposit, or the typed actor refs we want to acknowledge when we process these commands. And then we also have some messages that are responses. And we have several different responses, as you can see here. This is an actual actor implementation. So it looks quite a bit different than the standard classic actor API. You no longer implement a base type and implement the receive block. You just call this these factory methods from the behaviors type. So this is the most common one you use, the receive message factory method, to implement the logic, the business logic for your commands. So we have this partial function that we're passing into it, just using regular old pattern matching to decompose the members of that type. And for the deposit, we're just sending an acknowledgement when we receive it, and then we're updating our balance for the account. And we do that by returning a new behavior. And this new behavior is just, in this case, a recursive call back to open account. And we pass in that new balance by just appending it to the existing balance. And then when a new message is processed, it's going to have that updated state readily available. In the get balance command, we're doing a similar reply to, where we're actually sending the balance back to the requester in this case. And then instead of updating state, because there's nothing to update, we just have this shortcut method to return the same behavior instead of just calling open account with the same balance again. We can just use this. So when you return a behavior like this, you're doing a state transition, but you can do a more powerful state transition that implements a new receive block with new business logic for the commands you want to process. So in this example, we're going to add a feature to freeze accounts. So we add a new command to our message protocol, this freeze account message, and a new type of response for when actors try to withdraw or deposit funds from into the account. So in our existing open account actor, we implement this new command. So we just acknowledge the command's process, and then we return a new behavior. So this is a behavior with the same signature as open account, but it's called frozen account. And it has a balance because when we have a frozen account, we still have money in it. And in the implementation of that, we have the same get balance method, or sorry, implementation, which is just returning the balance to the acknowledgement actor. But the deposit and withdrawal implementations are different now. Instead of actually changing the balance, we're signaling back to the caller that the account's frozen, there's nothing we can do, and just return the same behavior. So Akka persistence typed is the counterpart of Akka persistence in the classic API. It has a new API as well. So it's a little bit different than how classic Akka persistence worked. So in classic, you had a persistent actor base type that you extended, and then that would give you access to the persistence API. So Akka persistence is basically an implementation of event sourcing, which is a pattern from the CQRS set of patterns, the command query responsibility separation patterns. So because it's an implementation of event sourcing, the typed API was specifically designed to include more precise terms that are relevant to those patterns, to event sourcing and CQRS. So the message protocol for an event source behavior has more types for you to consider in your message protocol. So you have your commands, which are pretty much the same as our simple example we saw before. And then events are created after a command has been successfully processed and are eventually stored into an event journal in a persistent state in a database somewhere. The state is an accumulation of event state changes. And this is important because if we want to reconstitute our state, we can do that by just reprocessing events from the event journal. And then reply is an optional thing we can do. Once the command's processed, we can do a reply to the caller. So here's an example of some of those types, or some of those messages implemented in our banking domain again. And this diagram shows sort of the workflow of what's happening in Akka persistence. So we're going to use the actor ref. We have an actor ref on the caller side of this event sourced actor that's shown in the middle. And we're using a interaction pattern known as the ask pattern. And this is a way to model a request response with an asynchronous response to a message that you send to another actor. So in this case, we're sending a command, and it gets processed by a command handler in the event sourced actor, which is basically just a user-defined function that processes the command somehow in any way you want and produces the event. And then the event is passed along to whatever Akka persistence plugin you're using. So Lightbend maintains two main ones, which are Cassandra and JDBC plugins. And then those plugins will serialize the event and it gets appended to this append-only data structure. So in this case, a table in the database. After the event's persisted, we optionally send a reply back to the caller. And an effect is passed to this event handler, which is another user-defined function of the event sourced actor. So this effect is basically a type that encapsulates the event as well as the state of this actor. And its job is just to apply the event to the state in order to generate a new state that we return in the event handler and that is used in future commands that are processed by this actor. Akka Cluster sharding. So this is an important subject to cover because a lot of the other features I'm going to talk about are based on it. So sharding is a similar concept to partitioning within a database, but instead of data, we're distributing actors across an Akka cluster. There's four main components to sharding. There's entities, which are basically just actors. There's shards, shard regions, and the shard coordinator. Sharding ensures that at most one instance of an actor entity is running on the cluster at any given time, and shards are distributed across the cluster according to a shard allocation strategy. Each shard has a subset of the entities and therefore handles a smaller percentage of the load, which helps balance resources and increase resiliency across the cluster. So a common use case for sharding is when you want to distribute state and processing of your entities. So if you need to represent a lot of stateful actors, you might need more resources than that can be provided to a single JVM instance, or you want to use more economized server instances. So in that case, you can create an Akka cluster that spans multiple virtual or physical machines and spread those stateful actors across your cluster instead of a single server. And then to access these entities, they have an entity ID, which is just a logical identifier that we can use to communicate with that actor. But we don't need to know which shard that entity is in or what physical machine it's running on. We can just send a message to a particular entity ID, and Akka is going to take care of the routing for us. This is known as location transparency in Akka, and it's one of the it's one of the nice features of Akka Cluster that kind of abstracts away the actor system across this cluster of machines. So the entities are the basic unit in sharding. They're an actor, like I said before, and they represent a single data type in your domain. So they could be a unique device if this is a IoT type of application, or it could be a user account. For example, you could have 10,000 users represented as 10,000 sharded actors, each with their own unique entity ID. Shards encapsulate a subset of those entities, and they'll create the entities on demand. So whenever there's a message destined for one of these entities, and it's not already running, the shard's going to instantiate it. And the number of shards is user defined. Each shard's going to have its own unique ID. And you can have multiple shards running on one cluster node, or there could be none. So you could have 0, 1, or many shards running on a single cluster node. It just depends on how many shards you have and how many nodes there are and what your sharding allocation strategy is. And then the distribution of entities to shards is defined by a user function, which is just a hashing function, usually of the entity ID. And the default is provided where we just take the hash code of the entity ID and its absolute value, and then modulo that by the total number of shards. And that calculation is going to return a shard ID that we can use to, or that Akka will use to assign or route a message or assign an entity to a shard. Shards are then distributed into shard regions. And when a message is sent to a region, it's going to look up the shard for an entity. And if it doesn't have that shard, then it gets forwarded to the appropriate node and its shard region. There's two types of regions. There's the local mode, which is basically the one running within the same JVM. And if a message is sent to a local region, then it will take care of creating the entity within its own JVM and sending the message to it. The proxy regions are basically a gateway to another local shard region that might be running on a different node. So it will just forward messages along as appropriate. And then finally, the coordinator uses a customizable shard allocation strategy to determine which cluster nodes host which shards. But you get a default strategy out of the box, so you don't have to actually define one. It's a cluster singleton, so that's a feature of Akka Cluster that means it'll only run on one node in the cluster at a time. And if the node running the coordinator goes down, it's going to come back online on another node and have its state rebuilt. And that state's either backed by Akka distributed data, which is a cool set of data structures we don't have time to get into, or you can use an Akka persistence plugin, like we were showing in the last section, and use an event journal to rebuild its state. Rebalances happen automatically if, for instance, a cluster node goes down. Any shards that are hosted by that down node will be rebalanced to the surviving nodes. So this is the start of the new features. These are net new, like since Akka 2.6, there wasn't any equivalent in the classic actor API. So the external shard allocation strategy is a way to control the shard to Akka cluster node map. So this is a nice API to expose if you want to follow the partitioning strategy of another distributed system. So the canonical example that we've developed a reference project for is when you have a Kafka consumer group, which has Kafka partitions assigned to it. We want messages that are consumed from those partitions to end up on entities that are hosted on the same node as that consumer. And by doing this, we reduce intercluster message traffic. So when in the case where, well, we'll see it in the next slide. So in the case where a consumer is on a cluster node that is that has different shards than that processes. Sorry, this example shows it more clearly. So in this case, we have a Kafka cluster, and we have just two nodes represented, and there's two Kafka consumers running. So on this first node, we have a Kafka consumer group. It's assigned partitions 7, 8, and 9, and so it's obviously consuming messages that are on that partition. But when it receives this message, it has a message key, which we also use as our entity ID, and we have a similar a user sharding function to assign this message to a shard. So in this case, the shard is the message is destined for shard B, but it ends up on this Akka node where shard B doesn't exist. So when that happens, the message is going to get sent to the shard region. It's not going to find shard B in this region, so it's going to use that location transparency principle to propagate the message across Akka cluster to the appropriate node. And that's where the extra network hop comes into play. So ideally, the consumer group member on the node where it is on the node where the entity exists, and then this extra network hop wouldn't have to happen. So what we have is in the Alpakka Kafka library, which is a Akka streams to Kafka library. We have this new external shard allocation strategy just to marry together Akka and Kafka partitions. So the way it works is it will calculate the total number of partitions in a consumer subscription and use that information in a new sharding user function that you can use with Akka Cluster sharding. And then when a consumer group rebalance occurs, we regenerate the Kafka partition to Akka shard map, and we move shards to the nodes where those consumer group members live. So we don't control where the partitions go, but we control where the Akka shards go on our Akka cluster. So by doing that, we can go back to this example, and when we're using that strategy, we consume the message and process. We have this shared user sharding function to find shard B, which is running on this cluster node. So we don't need to send it over Akka cluster and incur that extra hop. Akka projections. So in basic terms, a projection is a data transformation from one system to another. And the Akka projections library is a more advanced version of what we call readside processors within the Lightbend framework. But Akka projections is a library, so it addresses a lot of the shortcomings of the readside processors within Lightbend. And because it's a library, you can just use it in your projects as is. You don't need to bring in a whole framework to use. And basically, it's used to create the read side or the query side in a CQRS system. So projections will take an Akka streams source input. So this could be an Akka persistence events by tag query, or it could be an Alpakka Kafka consumer source. It doesn't matter. And then we can distribute these projections to scale up its processing across different cluster nodes. So here are the three basic components of a projection, two of which are just part of the library itself, the source provider and projection. These are things that you can just pick the ones that are available and use them within your project, or you could implement your own if you really wanted to. The source provider is the source of events. So it could be a Kafka consumer subscription or the Akka persistence event journal, like I was saying before, or it could be any other source. The only caveat is that the events or the messages that we're pulling out of that source are associated with an offset. The events are delivered in an event envelope, which contains the payload, the event, and the offset. And then the handler basically encapsulates a user transformation to the projection target. And the projection target is really up to you. It could be a Kafka topic, it could be a table that we perform CRUD updates on, or it could be a message to another actor. It's up to the user. And finally, you choose the projection you want to use. And the projection defines the implementation of the offset store that we use to store offsets associated with the event in order to provide several message delivery guarantees. So we have two main implementations of projections. One's for Cassandra, one's for JDBC, and for various reasons, they don't both support all of the message delivery strategies. But I won't get into that. You can feel free to ask me more about that after the talk if you like. So the most used strategy is probably the at least once. So with this, you can configure when to persist an offset. So you might want to persist it every n elements or after a certain duration or whichever comes first. In this example, we're saving an offset after 3 elements are processed by the handler. And since persisting an offset requires a round trip to the offset store, we can economize the writes to that offset store by writing less frequently. But that comes with a cost. So as its name implies, the user handler is run once per event, but because the the offset isn't stored every event. If we had a failure before the next offset is stored, then there's a possibility of replaying some messages. So that's why it's called at least once, because we'll process messages at least once. And at most once sort of changes or flips this this workflow where we always store the offset before we process it in the handler. And by doing this, we can guarantee that a message is processed at most once. And if a failure occurs before the handler is processed, we could, the failure scenario would be we skip processing a message, but that might be acceptable in certain use cases. And then exactly once is sort of a kind of mythical message delivery strategy that we can sort of implement with a number of caveats. So if we have an offset store that if we use a relational database that supports transactions and we have the offset store and the projection target in the same database, then we can combine those into a single transaction. And it's an all or nothing operation that we can commit or roll back. So that's how we achieve those guarantees. So here's the code example of how you would create a Cassandra projection with at least one semantics. So you just give it an ID, you give it a source provider. So in this case, we're using events by tag to stream from a persistent or a event journal. And we define a handler. And in this case, it's just a simple functional handler, but you can also use an actor here, or you could use an Akka streams flow to process the messages. The sharded daemon process is another net new feature. And I'm going to talk about this in the context of Akka projections. So a sharded daemon process allows us to distribute work evenly across a cluster. And it uses cluster sharding to distribute a predefined number of worker actors across all of the cluster nodes. When the cluster node joins or leaves, a rebalance is going to occur and redistribute daemon process actors to remaining available nodes. So like I said before, I want to explain this in the context of projections. So if we want to use sharded daemon processes to scale up projections, to run them on many nodes, we have to first make sure that the data in our event journal is partitioned so that we can read unique data for every instance, every projection instance that we instantiate. So we first need to modify how we persist data, and we have to create these slices as tags, and we have to define a number of tags that we want, the same number of tags that we want to run as the number of projection instances. So you have to define this beforehand. It's similar to defining the partition number for a Kafka topic. So we define those tags, and then with the event source behavior, we have this with tagger method where we just pass along the selected tag. I'm hearing myself speak. Not sure why I'm hearing myself speak. I'm just going to take my headphones off. So using the sharded daemon process, we can we can distribute the projection across Akka Cluster. So we just define the number of instances of projections we want, and that's basically the number of tags we have. And then this behavior factory is just taking a projection behavior, which is a thing out of the projections library, and we pass the projection into it, and we pass this integer value, which represents the ID of that sharded daemon process. And that ID is basically just a number from 0 to the number of processes we have. So we can use that to determine which set of tags we want to stream for that instance. And the last big thing I'm going to cover is a split brain resolver. So this isn't a new feature, but it's something we open sourced recently. So the split brain resolver is sort of the missing piece of the puzzle when running Akka Cluster in a production environment. It provides a set of strategies that have been battle tested by Lightbend customers over a number of years. And it was commercial for a long time, but for a number of reasons, we decided for the good of the Akka community, we'd open source this component and make it free for everybody to use. So it's a set of strategies to handle network partitions within an Akka cluster. And a partition occurs whenever a node can't establish a network connection to other nodes. A node might not be reachable because of that network partition, or it could be because that JVM with that node shut down unexpectedly for whatever reason. There's no way we can tell which case happened. We just know that that node is unreachable. So to handle these situations, we use SBR. And in the event of a network partition, there could be a case where we have a split brain. And that basically means that we have two sides of our cluster that exist. And one of them has to, and both of them are kind of working independently. And that's a bad situation because a lot of features in Akka Cluster will stop working if they don't have that complete view of the cluster. Features like cluster singleton and cluster sharding. So there's a Kubernetes strategy available, and it basically just uses a distributed lease to determine what cluster nodes are allowed to survive when a network partition occurs. So it just uses a custom resource in Kubernetes, and the pros to the strategy are that it's safe. It's safe to use because it relies on an external arbiter to store and coordinate access to the lease. But some of the downsides are it requires Kubernetes obviously to run, and it's relying on access to the API server to always be available. And the API server is pretty resilient, but it's not totally infallible. So if the API server does shut down and we can't refresh our release, then all nodes are going to shut down. So, but if that happens, then your API server is inaccessible. That usually means there are bigger problems happening in your cluster. So in the example we have here, we have a 5-node cluster. The cluster is formed, and a membership information is created by all of these nodes sending heartbeat messages to one another using the gossip protocol. And by sending these messages around, they build up a membership information, so they know what the cluster looks like. And then one node on the cluster is responsible for updating the lease. If the network interruption happens, then heartbeat messages will start to fail, and nodes can't communicate with one another. So to get out of this situation, to decide which part of the cluster becomes the main part of the Akka cluster, we have to wait for a configured time span for heartbeats to hopefully recover. But if they don't, then we implement the strategy. So in this case, each side has a last known snapshot of what the cluster looked like. So it knows based on which nodes it can still communicate with if it was in the minority or the majority. And for the nodes that are in the majority, it's going to send an attempt to obtain the lease right away. But the minority side is going to wait a few seconds in order to give the majority side a chance to get the lease first, because ideally we want the majority side to win. So if the majority side wins, then the minority side will shut itself down, and then the cluster is basically back in a healthy state, although with fewer nodes. And then the last thing I'm just going to plug is this Akka platform guide. It's a set of documentation that describes step-by-step how to build CQRS systems. And it's using components from the Akka toolkit, obviously, and it covers a lot of the same things I talked about today. It also talks about best practices when it comes to deploying these things into production. And the platform guide's a first-class set of documentation. It's going to be kept up to date with new best practices and new features as they're added to the Akka toolkit. So this is just a list of resources if you want to grab these slides after the presentation to learn more.